volt voltage supply. Okay, and we are going to, in 10 minutes or less, do the following 5 things. Number 1, we're going to figure out what is the total gain in the circuit. Pretty easy. We're going to do number 2, what is the total or the equivalent capacitance. I'm going to go back and forth between total and equivalent, and I mean the same thing when I say total and equivalent capacitance. And then we're going to get the total charge. These are the things that I like to call the big 3. The total voltage, the total or equivalent capacitance, and the total charge. Then, after that, we can get the charge stored on each capacitor, and then we can get the voltage drop or the potential difference really across the plates of each capacitor. And we're going to do all 5 of those things, as I said, in 10 minutes or less. And the first thing we're going to do is figure out what is the total voltage. Now, this is very easy. We have one battery right here. It's 6 volts, so that means the total voltage in the circuit is 6 volts. Basically just saying we have a 6 volt battery. I want to make sure everybody knows that. The total capacitance. Now, we have capacitors in series. These are not capacitors in parallel. If these were capacitors in parallel, then we would simply add up 12, 6, and 5 and get 23. But we have capacitors in series, so we must use what I like to call the 1 over equation. The total, the equivalent capacitance, is equal to 1 over the equivalent capacitance is equal to 1 divided by the capacitance of capacitor number 1 plus 1 over the capacitance of capacitor number 2 plus 1 over the capacitance of capacitance number 3. Okay? You don't add them up. Sorry about that. That's parallel capacitors. Series capacitors, we use this nice equation, and we can just plug the numbers in. We get that 1 over the equivalent capacitance is 1 over 12 plus 1 over 6 plus 1 over 5 farads, and you can do that right on your calculator. 1 plus 12 plus, 1 divided by 12 plus 1 divided by 6 plus 1 divided by 5, and you get on your calculator that 1 over the equivalent capacitance, or 1 over the total, is equal to 0.45 farads. That is not, I repeat, not the equivalent capacitance. That's 1 over. To get CT, or to get the equivalent capacitance, you have to take the reciprocal of both sides. So I'm just going to flip this one over, and I get CT over 1, which is CT. This is actually, if you think about it a little bit mathematically, 0.450 over 1. I flip that one over, and I get that CT equals 1 over 0.450, excuse me. So that means that the total capacitance, the equivalent capacitance, is 2.22 farads. All right, that means that in order to get 2.22, basically all I do is I take 1 over this number, 1 over 0.45, or on my calculator I do 1 divided by 0.45, and that gives you the total capacitance, which is 2.22 farads. Okay, that's the total capacitance. Now we get the total charge. Now, the way the total charge works is, in order to get the total charge, we're going to use the capacitor equation, what I like to call. The charge is equal to the capacitance times the voltage. Q equals C times V. We want to find the total charge, which is QT, total. In order to do that, we have to use the total capacitance. That's why I like to call it total. And we have to use the total voltage, right? You're going to do the totals, use the totals. You're going to find one of the totals, use the totals. So Q is therefore equal to 2.22 times 6 volts, and the total amount of charge stored in that circuit is 13.3 coulomb. All right? So we got the total voltage, the total capacitance, and the total charge, and now we're going to go on and do the voltage stored, the charge stored on each capacitor. Now this is relatively easy because we already found the total. You see I have the total voltage, the total capacitance, and the total charge here. We want to know what is the charge on each capacitor. That's relatively easy to figure out because the rule for capacitors in series as it relates to charge is that the total charge is equal to the charge on each of the capacitors. Or since we're trying to find the charge on each capacitor, we would say the charge on each of the capacitors is equal to the total charge. Now, why is that? Well, I made a very nice video that explains why that is. I'm not going to go into it in detail, but let's just realize that the charge on each capacitor is equal to the total. Well, we found the total already, so we know the charge on each. The charge on number 1 is equal to the total, and that's 13.3 coulomb, and so on and so forth. The charge on number 3 is also equal to the total, which happens to be 13.32 coulomb. All right? So we use this rule. We found the total first. That's generally the way you do it. You're given a circuit, you find the total capacitance, and then you know the total voltage because it's just a 6-volt battery, and then you can calculate the total charge, which we did on the previous slide, and then we know that the charge on each of the capacitors is equal to the total. So, okay? Okay, next step is what's the voltage across each capacitor? Okay, now we have 3 capacitors in series. We have 1 voltage supply. Just like resistors in series, the charge is going to get, the voltage or the potential difference is going to get spread across these 3. So we would say that the rule for the voltage and series capacitors is the sum of the potential differences across each capacitor is equal to the total being 6, the total being 6. Now, in order to do this, we're going to have to calculate using our capacitor equation. Q equals C times V. We want to solve for V. So that means, for example, for number 1, the potential difference across the plates of capacitor number 1 is Q1 divided by C1. If we're going to find number 1, we have to use Q1 and C1. Well, Q1 is equal to the total. We did that on the previous slide. C1 is the capacitance, so it would be 13.32 coulomb divided by the capacitance, which is 12 farads, and you get that the voltage is 1.11 volts. Number 2 is basically the same thing. The charge is the same. Remember, the charge on series capacitors is the same as the total. We calculate the total 13.2 divided by the capacitance, number 2, 6. You get 2.22. The next one, the voltage on 3 is the charge on 3, which is 13.32, divided by the capacitance of 3, which is 5, and you get 2.66. Now remember, the rule here says that the sum of the voltage drops, the sum of the potential differences is equal to the total voltage. So that means 1.11, 2.22, and 2.66. That'll add up to 6 volts. And if you add them up, they do. And if they do, that's good because they're supposed to. And that means you can feel good about what you did because you probably did it right. Okay? So that's...
Now for the parallel, the next video, see for the parallel plate capacitor.
Charge, the voltage, and the equivalent capacitance for capacitors in parallel. Now this is the circuit we're going to use, and I'm going to go through all of this one step at a time, and these rules and these calculations all apply regardless of how many capacitors we have in parallel. Typically it's shown as 3 capacitors, but whether we have 1, 2, 3, 4, 5, or many more, we apply the same rules and the calculations in the same way. And I'm going to go through and we're going to do 5 different things in this video. First of all, we're going to figure out, which is very obvious, or say what the total voltage gain is in this circuit. Then we're going to get the total or the equivalent capacitance. Okay, total equivalent, that's the same thing to me, the total capacitance of the circuit. And then we're going to get the total charge stored in the circuit. Those are our 3 totals, the total voltage, the total capacitance, and the total charge. And then after that, we're going to get the voltage drop or the change in potential, electric potential across each capacitor. And then we're going to get the charge that is stored on each capacitor. Okay, those are the 5 things we're going to do. We're going to do all that, and hopefully it'll be less than 10 minutes. Okay, the total voltage gain. That should be relatively straightforward. We have 1 battery over here. We have a 12-volt battery, and we just have the total voltage is 12 volts. Okay, so that's not that hard. Number 2, the total capacitance. What is the total or the equivalent capacitance? Same thing, equivalent total capacitance for this circuit. Well, we have 3 capacitors, 1, 2, and 3, a 12 farad, a 6, and a 5 farad capacitor, and they are hooked up in parallel. And it is very easy because the rule or the equation is the total capacitance But once again, the equivalent capacitance is equal to the capacitance of the first one plus the capacitance of the second plus the capacitance of the third capacitor. All you do is add them up. So that's 12, 6, and 5 farads. Add them up and you get that the equivalent capacitance, the total capacitance, is 23 farads. All right? Okay, next. What is the total amount of charge that is stored on this circuit? Now, we could go through and figure out the charge on this one plus the charge on the second plus the charge on the third and then add them up and get the total. And we're actually going to do that later. But first of all, we can easily get the total charge by using our capacitor equation. Q equals C times V. And since we want to figure out the total charge, we have to use the total capacitance, or the equivalent capacitance, and the total voltage. All right? And we can do it all in one step. And so that means that the total charge is equal to 23 farads, which we got over here, times 12 volts, which we got from our battery. Okay? Total capacitance, total voltage, multiply them together, you get 276 coulombs of charge. All right?
Friend, these are the very important example for the parallel plate capacitor and the series plate capacitor, because in your GTU exam many times the problems are based on the capacitor, series and parallel. So these are helpful for you to finding the parallel plate capacitor for the capacitance, voltage and the charge storage in that, as well as for the series plate of the capacitor. Now just go through the next question. This is one example. The three resistance 10 ohm, 20 ohm and the 30 ohm are connected in the parallel across the 240 voltage supply. These are the parallel resistor and these are given with the 240 voltage supply. So now calculate the current through each resistance. First of all, we have to just find out the I1, I2 and I3 for all these three resistors. The next one is to total current. This one, first one is the individual current. Now the next one is the total current, and the last one is the power dissipated in each resistance. A question contains the 4 marks. Now first of all, just making the circuit for that. 3 resistor, (10 ohm resistor), then 20 ohm, and 30 ohm are connected in parallel, and these are given. The total supply is 240 voltage. So now whatever the current passing through is known as our total current IT. But whenever this current is flowing from here, that is suppose I1, like I2 and like I3. So we have to just find out the I1, I2 and I3 and the total current and the power dissipated in that circuit, and the power is I square R, or you can find like that P equals to V into I. Both the equation are used for the power dissipation. So now just go through the example. First of all, just finding the current I1, the current I2 and current I3. These are the responsible current or respected current flowing from the 10 ohm resistor, 20 ohm resistor and the 30 ohm resistor. First of all, I1 is the current passing through the 10 ohm resistance. So by using the Ohm's law, I1 equals to V by R1. Our V is 240 voltage and R1 is 10 ohm. So by dividing 240 volt to the 10 ohm, we are getting that I1, that is 24 ampere. The current unit for the current is ampere. Now similarly, that is I2, that is the current passing through the 20 ohm resistance. So by using again the Ohm's law, I2 equals to V by R2. Our V is common for all these three resistance because these resistors are connected in parallel, and we know that voltage is the same quantity for all this equipment or the devices which are connected in parallel. So V is 240 and R2 is 20 so by taking the division 240 by 20 we are getting the I2, that is 12 ampere, and similarly that is I3 equals to V by R3. Again this is Ohm's law. As we all know that if we are giving the I, V and R ratio, then this one is very important law. Ohm's law is very important law in electronics to finding any one of the quantity given to you. So by using the 240 by 30 we are getting that I3 equals to 8 ampere. So now I1, I2 and I3, by taking the summation of all these three current, we are getting the total current, that is IT. That one is I equals to 24 plus 12 plus 8. So our total current passing from the circuit is 44 ampere, and this 44 ampere is divided into all these three resistors R1, R2 and R3. Now the power loss in individual circuit, that is suppose power loss in 10 ohm, that is P1 equals to, again we are using the power loss equation, that is P equals to I square R, but here we have to just finding the current power loss in the R1 resistor. That's why P1 equals to I1 square into R1. Our I1 is 24, so by taking 24 square and multiply with the 10 ohm resistor, we are getting that P1 equals to 5760 watt. The watt is a unit for power. Now next one, that is the power loss in 20 ohm resistor, that is P2 equals to I2 square into R2. Our I2 equals to 12 ampere, that's why 12 into 12, that is a square, into the 20 is the R2 resistor, so we are getting that 2880 watt. Similarly we can also find out the P3, that is the power loss in 30 ohm resistor, that is I3 square into R3, and we are getting that 1920 watt. So now these are the individual power loss in 10 ohm, 20 ohm and the 30 ohm resistor. So by if you want to find out the total power loss in the circuit, then by taking the summation of P1, P2 and P3, you are getting that all over the total power loss in the circuit. Now the next question, again it's a example. The three resistors 20, 30 and the 50 are connected in the star form. Just find out the equivalent delta connected resistance. Here you have to just using the delta to star and the star to delta transformation. First of all, the 20, 30 and 50 ohm resistor are connected in star form. So by performing the star to delta transformation technique. Now let's start with this example. First of all, R12 equals to R1